the title is Asymptotic higher ergodic invariant. Russia, my institute names is terrestrial magnetism of ionosphere and radio wave propagation. There are some magnetic tubes here, and the subject of my talk is to introduce some statistics of complicity of such an object. But the focus is that I will be studying what are inside the tube, but not so much how these tubes are organized globally. So the invariant will be detected by the line position, but not by the position of the tube itself. So the first basic idea was introduced by Monastyrsky and Retich in 80. They are applied Milner invariant for MHD. And it was organized the competition 20 years ago, and I was involved in this competition by Alexander Ruzmaykin, and we are proposed one of the integral of a Massey type. This integral looks like following. If we take two magnetic tubes, the vector potential A1 and A2, then we can organize such a field. This is a divergent free field. Because this last term organized like this, that this equation is satisfied. And then there is a vector potential, and we can do the helicity of this second order magnetic field with some extra term. This is order 3 invariant. It means that this invariant can detect the defects in codimensions 3 in point of view of Vasiliev. And this is degree 4 because if you take the scale b goes to lambda b, that this expression will change lambda in power 4 times. So as usual, the degree is the order is twice the degree. For example, for the helicity, the order is 1 and the degree is 2. But here we have 3 cross 2 is 6. 6 is greater than 4, and this is very this is interesting. Then I'm not an expert in British poetry, but the only I can say that there is the limerick, and the subject of this limerick, this is something about Sato-Levin invariant. Now, what's wrong with Sato-Levin invariant? Everything is well, but this invariant is partial definite. So if you assume that the magnetic tube is linked with linking coefficient 0, nothing reason to do something else. But this is very restrictive condition. But fortunately, we can do some modification of the Sato-Levin invariant like this. If you take 3 tubes, by the same idea, we can organize the vector potential divergent free, and then we can define the invariant M, which is totally defined. This is invariant organized like a Massey product, and so this is more or less standard expression in MHD. But this invariant totally defined. This invariant has order 12. It means that this is very high order invariant, and the degree of invariant is 7. This is a mistake. Order 12 and the degree in point of view of Vasiliev is 7. So we have just have a lift. So 7 cross 2 is 14, and 14 is greater than 12. This is important because there is a chance to take the ergodic. This invariant can be generalized for magnetic line, and also because this invariant is totally defined, the question is how we can express in the standard term. So if you take 3 magnetic closed line L1, L2, L3, there are the following picture. We have linking number named like this. This is the first coefficient in the Alexander polynomial. Then we have the coefficient C1 of L1, C1 of L2, C1 of L3. Then we have a coefficient of the pair. Then we have a coefficient of the triple. And the meaning of this invariant is following. You have a combination rather difficult. The main term of this combination looks like this. And plus some extra term which involves these two guys. Then plus some combination of these guys, and this some polynomial which give us a renormalization. So this was suggested by a work by Sergei Melechov. But in this printed, they use the Alexander polynomial, multivalued Alexander polynomial, and I was stopped on the first page, and the paper contained 20 pages. So I think the structure of the relation between Massey product and Alexander polynomial is very interesting, and but this is not a subject of my talk. Now, what we shall do with this invariant? We will apply the philosophy by Vladimir Igorevich Arnold is following. Arnold in 1884 formulated the following problem: to transform the ergodic definition of Hopf invariant of a divergent free vector field to Novikov theory, which generalized Whitehead product in homotopy group of sphere. This is rather strange point, because this is indeed generalized Whitehead product. As you see, the generalization comes that the commutator in the Milnor tower, which is defined by the weight, and the weight is nothing else but the linking number. And so Novikov theory means that we have just a generalization of the Whitehead product. And so what I'd like to remind the definition of Arnold asymptotic Hopf invariant. Asymptotic Hopf invariant looks like this. If we have two closed curves, it gives nothing interesting, because here we have the integration of the degree of the Gaussian map, and then this is just the linking number of the two lines. But it works in the case when the line are ergodic. So if you take the integration, then we must take the limit when the length of the light tends to infinity, and so this is the definition. X is the magnetic flow. J is a one parameter diffeomorphism family which spanned by the magnetic field, and this is just magnetic field itself. It sits into this integral. This is misprint, and then the meaning of helicity in point of Arnold is following. This is the helicity density because this function is integrable by the Birkhoff theorem, and so the mean value of helicity density is nothing else by A cross B, as usual, helicity invariant we had from Kelvin paper. Now this is the theorem. This is some remarks about the dimensions. Now I'd like to define the mind construction, how I'd like to generalize. So idea is very simple. I'd like to define the configuration space, and then I will organize the flow on this configuration space, and the mean value of this flow is just high order helicity invariant. The configuration space is following. Space itself is a space of collection of the if we take the finite collection of the point in the space, we can issue the line in my construction R is equal to 3 because I have 3 components, and then I take randomly R is a very big number. I take the randomly some collection on point of each line. Then I will say that the asymptotic, the invariant, the functional is asymptotic if they obtain like a ergodic mean value of this function, which is well defined of the configuration space, where the Rt tends to infinity when the line, the length of the line goes to infinity. Then by Birkhoff theorem, the invariant is well defined, and if I start with integral expression of some integral of links or nodes, if I apply such a construction, then I can generalize this invariant from the combinatoric stuff to the ergodic. And there are 2 remarks. This I just was mentioned, that the asymptotic invariant is the ergodic mean value of the integrable over the configuration space, which is equipped by the commuted flow. The flow organized like this, that each point goes through the line independently. And a finite type invariant using, and we try to apply the integral formula I was mentioned below to work with. And nice things that this invariant is very well organized, so all the terms are quite friendly to Maxwell equation, and no problem with partial definity, because in the ergodic limit it would be very difficult to consider when the first order linking number is trivial to construct the second order. Now, but there are several problems. The problem is that it is very difficult to organize to prove that this ergodic invariant is ideal MHD. And so, if I to formulate the precise result, I have to do the following. As you know, the ergodic magnetic flow satisfies the Poincaré recurrence theorem, so it means that almost arbitrary point goes almost the same place for some time. But if I take the strictly assumption that arbitrary point, or almost arbitrary point, goes just the same time, then all the lines of magnetic field are closed. And so I can prove that this invariant is well defined only for a magnetic field with all the lines are closed. but the main theorem said that this exists in asymptotic invariant M for in general case. But if additionally this magnetic field satisfies this recurrency condition, then this magnetic field is just preserved in ideal MHD. There are three remarks. The first the strategy is very simple. I take this expression for M and then I will split cut off into elementary algebraic combination, and for each combination I will apply just Arnold philosophy to take the ergodic invariant. And there are three different kinds of terms. The first typical is linking number with some power. This is this is the most easy situation, and all the last talk I will tell about it more detailed. So the idea that this is there are no problem with gauge transformation, and so this can be much easier than the second type of the term. The second type is organized like following. You take, in my example, for example, you take a product. This is a one form, this is a wage, this is two form again, and this is maybe some duality. But anyway, if we consider just for a vector field, this is vector field, and the scalar product of these two vector fields is just a term involved into integral, and this is just typical term which will be in all the integral of Massey type. And the problem is to generalize to ergodic case. I don't see this is difficult, but the gauge transformation for such a vector field will have to pay some attention. And the third integral is very difficult to prove. In my to organize into ergodic case, this term was introduced by Mikhail Berger in 19, and it was organized like this. This is just a function A1 AB over the line, and this is a scalar potential of the vector field which induced in my example from the second and third magnetic line. This function is not multi-defined, multi-valued, but single-valued function. But the problem is how we can organize in the ergodic limit this extra term. And there are some. There is a problem here, because if you take the configuration space for this term, it looks like this, and the ergodic flow can be organized like this, but I take the space, the configuration space is non-compact, and if I organize ergodic flow on non-compact space, there is a problem that the function is not integrable, and I cannot apply Bergov theorem. But if this flow induced from the compact configuration space, I can do. In this case, this flow is induced from the compact part, but we have a straight line, and so the orbit of configuration space looks like an incompact race. And in this space we have a function, and in the periodic case we just have a periodic function. The compact space is this is non-compact space, and even the function is not integrable, but the mean value exists because this is periodic case. And in quasi-periodic case I can do nothing but define the upper and lower limit for t goes to infinity, some alpha dt, where t is just a distance. There is a flow on configuration space, but this flow does not induce from the flow on the space itself. And this could be different. So the third term give us multivalued invariance. This space?
Or is it going to infinity with time?
This configuration space is like this. This is a square if we take the line L1, this is just the configuration space of the position of the line. This is diagonal, means that the flow organized like a magnetic flow along this line. And this extra, it looks like that we can do the shift, the point along the line. And I am not able to do it to induce this flow from the flow to the space itself. So I have the straight line, and I can prove the function I like to do integration is bounded from above, from below. But maybe these limits are equal, but I don't know. I'd like to. This is some example why the gauge transformation is difficult. But to keep my time, I will skip it. How many time have I? 20 minutes? 10 minutes? So now I'd like to do more or less detailed explication what we will do with Q monomial helicity. So this is just the first type summoned in this integral. The definition is following. We take 2 points in the space, we use the trajectory with time t1, t2, then we have a configuration space. In each line we put k points, and so this is configuration space of 2 k points, and this is a integral kernel. This is nothing else but the product of the Gauss integral, and then we will take the limit where t goes to infinity. This is the definition of Q monomial helicity, and the meaning is absolutely clear. So if you take the monomial helicity is just the average value of all arbitrary position of this to initial point of magnetic line, and this this function is nothing else but the function lambda, nothing else but the helicity density in power q. And so we have very clear statistically meaning of this term is when q is equal to 2 is just the dispersion of the magnetic helicity, and this is high order momentum. What the problem is? The problem is to prove that this is well defined. The strategy I have introduced goes well for high order helicity, and so it may be a good idea to investigate first this more or less elementary case, because all the arguments, but this goes well for the high order helicity. Now, what the theorem says, for almost arbitrary points there exists this number is well defined, and this function is measurable, integrable. So the first point is quite clear, because by Arnold's theorem lambda is well defined almost everywhere, and this is power q of lambda, and so if lambda well defined, that lambda in power q is also well defined. But lambda is very complicated function. This is not a smooth function, and the problem is if this function is integrable. The answer is yes, and I will show you the reason. Take the configuration space like this. The function is organized like this. I just mentioned. Then we have a integral organized like Gaussian integral in power q, and so the functional is well defined. Now the statement 1 is just proved, I mentioned by Arnold's theorem, and statement 2 goes from the following arguments. If I will take some function, arbitrary function, and this function can be estimated by the integrable function comes from the configuration space, from the domain itself where the magnetic field arises, and if I can prove such an inequality, then this function that means topological sense exists in the asymptotic limit. So the only problem to organize some more or less elementary non-equality which give us that this is well defined. This is the lemma I just said about. Now, what the main focus is? The main focus is that the integral kernel has to be smoothed. So I introduce the small parameter epsilon, and then if I take the integration, not the kernel itself, but the smoothing of the integral kernel with epsilon is very small scale. For this integral, I can prove that I can prove the estimation of this integral by means of the integrable function over the domain Q itself, U itself. There are elementary fact that this can be estimated by this, and this is power Q, and because of the smoothness, I have just logarithmic pole on the plane, and so in arbitrary power this function is integrable, and so this function give an estimation above the initial integral. So if I do the smoothness, the ergodic case change, and for individual trajectory I have could have quite different because it will be complicated. But if I take all the trajectory, then I have very small distance between the smoothness and the initial integral, because this is just a boundary problem, and the boundary of the cube have the dimension 1 less, and so the integral is very well estimated, and this integral, this function is integrable on the configuration space. This is very easy fact, proof that the high order momentum of helicity is well defined. And now I will end with some conclusion remark. So the first remark that the two monomial helicity is nothing else but the dispersion of magnetic helicity, and this is high order momentum. So at least it has a statistical meaning. This remark tells that maybe this is more useful. So if they ask about the practical significance of this result, I say that high order helicity have no practical significance, is only theoretically can be organized like ergodic Arnold invariant, because a very huge term. But this is technical problem to do it step by step, the simplification. But as about quadratic helicity, it could be useful for magnetic for induction equation with extra term. For example, if I take alpha term, and if I organize this integral like a ergodic invariant, I can do the estimation. This integral automatically is stable. So it means if I take some extra dissipation, then the dispersion of the magnetic helicity can be estimated by the Lipschitz coefficient. But because this ergodic case, I am not able to do it smoothly, and I think that smoothly it can be. This invariant is only continuous dependent on this extra term in the induction equation, which distinguish the ideal case to the non-ideal. And this extra term can be, so the distribution of the dispersion can be estimated explicitly using this technique. Now the third is about, yes, and the last is a conjecture. I think that this is nothing interesting if we have a magnetic tube and two magnetic lines from the three are dense in this magnetic tube. I think this integral has to be trivial. But it is still well defined, and this is not so obvious. But it could be work when the magnetic tubes links each other like Cantor set. So, so the situation could be the magnetic line could be very difficult configuration, smaller and smaller shape, but the ergodic line goes separately to other to different magnetic tube. I think this is all.
Questions? Yes, please.
So these are all integrals over points in the tubes, right? So in the usual integrals for the finite type invariants, you have to have integrals on the curves and integrals, the y integrals with one point in space.
Mm-hmm.
And the point is that if you don't do that, the boundary components don't meet up right to give you a cohomology class in the bigger configuration space. So how do you get around that here? Do you ever have exterior points, or?
I don't know the answer, but the answer, my expression, this your question is very complicated. So there is a guy from St. Petersburg named Podkaritov. He showed me the difference between configuration space organized like a point in the space and like a point in the line. If you like to take something high order which detects the right-hand link, for example, this is possible because this second term, the right-hand link was detected by this guy, and so we have to try to do it more delicate with configuration space, and my configuration space is just required to do the integrable first. I have to know the flow, and the reason. But if you take, if you like to take the integral itself, you cannot the equality, but non-equality, like in the quadratic helicity case. You don't know what the dispersion means, but you can estimate the dispersion by well-defined function, and the explicit estimation is just huge problem. And if you, I can tell nothing.
Oh, okay. So maybe the point is that if you have several tubes, then you can pick up higher link invariants this way, like your example of the Sado-Levine invariant and so forth. But maybe if you have a single tube, it's pretty hard to pick up anything other than like a power of helicity.
Yes. If you take separate tube, no reason to apply the ergodic theorem because it's just well defined. It's quite separately, and the integral for magnetic tube works well. So it's just the problem, the line inside one tube.
Right, you could have like 3 points in one tube and 5 points in some other tube, and within each tube you sort of do ergodic things, and then for the cross terms.
Yes, the cross term could be simplified, but I did not study it. If you organize like on the cross term, surely it can be just the same integral what I studied was at the very beginning.
Okay. Thank you.
Okay. There are no other questions. Let's thank both speakers this morning.